Let's see. We'll begin with a word of prayer as I get up here. Heavenly Father, we just thank you for this day. Again, I thank you for this class, and I just pray that this help session will be helpful and that we learn a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. So, you'll forgive me. I'm a little bit tired today, and so rather than looking at book problems, I'm just going to look at some old solutions I have, and if I inadvertently show you the solution to your current homework, well, I'm sorry. But, well, maybe that won't happen. Let's see here. So this is, let's see here, as a point of reference, this is actually my test 3. Oh, this is actually test 3 from fall 11, which I may or may not have posted. I don't know. But anyway, here it is. So if you wish to build a velocity selector which selects charged particles of velocity 1,000 meters per second, and it's constructed with an electric field generated by a voltage source with a difference of 1,000 volts across a 1 centimeter gap, like a parallel plate capacitor, then what magnetic field will you need? Find the magnetic magnitude B. Assume the fields are perpendicular to each other and the velocity of the incoming particles. So here's a picture. I've got my electric field like so. My charge Q is coming in like that. It's going to 1,000 meters per second. You got 1,000 volts between here and here. We want the magnetic force and the electric force to balance out so that it goes straight through, right? That's how we select. Otherwise, the electric force or the magnetic force is going to bend the motion off the straight path, and it's going to collide into the sides of the thing before it gets through. So we need QV cross B equals to QE, but here V and B are perpendicular, so we just give VB. The Q's, they be canceling, and that gives us B as E over V, but that is, that's the velocity, right? So we've got 1,000 volts divided by 0.1 meters, that's the electric field, right? And then, because we're in a parallel plate capacitor, so the voltage divided by the distance. Another way to look at it is the voltage is equal to E times D. So, yeah. Anyway, so 1,000 volts over 0.01 meters, that gives me the electric field. And then I multiply by 1,000 down here, which gives me 1 over 0.01, which is, apparently I need a 100 Tesla field to achieve this, this setup, which is kind of neat. So that's an example of a velocity selector. Here's another example. Again, this is from test 3 of yesteryear. So find the magnetic flux through the rectangular gate pictured below. Assume the gate is square with side length 5 centimeters. Assume the magnetic field's constant and has magnitude 3 Tesla in the positive y direction. Your answers will be in terms of angle theta. All right, so we have, well, there's my gate, right? There's my angle theta. And so here's a picture of the perpendicular to the gate and the magnetic field and theta. You can picture that down there. And so the part of the magnetic field which is giving us flux is B sine theta. And so L squared times the perpendicular field gives me this, which gives me 0.075 meters squared Tesla times sine theta, and that would be the flux in this case. So, yeah. You know, you could make this a Faraday's law problem. If I took the same problem and then I made the gate swing with constant angular velocity omega, as the gate swings, the magnetic flux through it changes because theta changes as a function of time. And I could calculate d phi b dt, and I could find the voltage induced in a swinging gate through this constant field B. That would be an interesting problem. Oh, I do that. Suppose the gate in the previous problem, you swing the gate smoothly from the x-axis to the y-axis over a 4-second time period. What's the voltage induced around the gate as it crosses 45 degrees? So Faraday's law is this, which is that. Now, but you know, I don't have any more details except to know that the average rate of change is pi over 8. radians per second would be the units here, which is why there's a 1 over seconds over here. So I take the, minus 0.75 meters Tesla squared. 1 over square root of 2 is the cosine of 45 times that. And so I get my induced voltage of 4.165 times 10 to the minus 4th volts, or if you like, 416.5 microvolts. And this is the magnitude. I dropped my minus for some reason. I mean, I wouldn't count you wrong if you put a minus here or put a plus here. I'm not, if I want to test on the plus or the minus, I'll ask you the direction of the induced current, as we've been talking about in several examples today. So problem 5, okay, what's here? So I like this. This is a good question. I learn a lot about what students understand or don't understand by asking this question on the test. Suppose you pull the loop pictured at a rate of 5 meters per second out of the region with a constant magnetic field 2 teslas into the page. If the loop is square with side length 5 centimeters, then A, what's the induced voltage in the loop? And B, what's the direction of the induced current in the loop, either circle clockwise or counterclockwise, circle your choice. All right, so if I'm pulling this loop down, right, then, originally we've got a lot of flux that's going into the page, right? So as you pull it down, you're decreasing the flux into the page, right? So the induced current needs to be such that it tries to increase the flux into the page. To increase the flux into the page, I want to go like that. And that is a clockwise current. So now to find the voltage, I have to introduce some variables. L is the length, X is the amount that's still in the region with the magnetic field, and so the magnetic flux is actually BLX here. Great. So if we differentiate that, we just get minus L dx dt. But dx dt is given to us. That's the speed, which is 5 meters per second. And so I put that in, and also the L and the magnetic field, and I get minus 0.5 volts, the induced voltage. The minus because it's clockwise. The current induced is clockwise. That's the significance of the minus. If we had a plus there, it would indicate a, well, anyway. So phi b into the page decreasing implies the current should increase the magnetic flux into the page, which means a clockwise current from the right-hand rule. All right, so I just talked about that. Moving on here, let's see here. This is an example I haven't done in class yet, but I will. I was going to do this today, but then we discovered the error in my previous solution, so oops. I don't think that I have posted anywhere, so if I hadn't made the mistake in class today, we couldn't have fixed it, but there you go. So this is a very common problem. You've got the magnetic field going into the page. Yeah, into the page, magnetic field. And you've got this bar that it can slide, right? And it's sliding with, oh man, my scan's kind of junky here, but the velocity v is going to the right, all right? So as that bar slides, right, the flux that is encircled in this loop that's formed by the bar and the rails, as this goes over, the area increases, and so does the flux. See, the magnetic flux is Lxb, where this is L, and that's the X, all right, X. So Lxb is the magnetic flux, and if I calculate the magnitude of the derivative of the flux with respect to time, I get Lb dx dt, but we're given dx dt is 14 meters per second here, and the magnetic magnitude is 0.8 teslas, and so we get 1.904 volts for the voltage induced. And then because we have the resistance, and we're assuming that the other part has essentially no resistance comparatively to the resistor, we can find the current by Ohm's law, electromotive, the induced voltage divided by resistance, which gives me 9.952 amps for a counter. And why is it counterclockwise? Because, all right, so you're increasing the flux into the page, right? You're increasing the flux into the page, so the induced current wants to increase the flux in the opposite direction, out of the page. So the induced current has to go this way, which is counterclockwise. Yeah. All right, so this is based on the last problem of the last test. See, I take requests. Oh, this joke is lost to time, but I'm sure it was hilarious for these students. A long cylindrical wire has radius 0.1 centimeter and carries a current of 67 amps uniformly distributed across its cross-sectional area. Find the magnetic energy per unit length within the wire. Oh, well, we're not to this material yet. I should probably come back to this, but just to tell you briefly. No, let me not do that today. I mean, there's a formula for energy stored within a magnetic field, just like there was a formula for energy stored within an electric field, and that's what this problem's about. We also haven't talked about the pointing vector, so I guess we might come back to that some other day. Circle 1, true or false? The magnetic force does no work on moving charges. Well, the magnetic force is FB, and so the work done by the magnetic force would be FB dot V. But what is FB? Well, it's QV cross B, which means that V and B are perpendicular, so the magnetic force dot the velocity is 0, which means, yes, the work done by a magnetic field is 0. It can change the direction of the motion, though, right? There's Maxwell's equations. We've talked about most of this already. We talked about this, we talked about that, talked about that, talked about this. This we have not discussed yet, and we will sometime soon. Okay, back in this particular phase of 232, I was still teaching some optics here, which I am not teaching in lecture anymore, so don't worry. That just gets covered in lab. I don't cover it in lecture, I don't think. Inductors, we haven't got to inductors yet. I don't know if we ever get to optics in here. I don't think I do. Well, we'll come back to RLC circuits later. This one we worked in class. You know, you have a long steady current, you've got a loop. What is the, you know, what's the flux for one thing, and then what's the induced voltage as a function of R. Supposing you pull it away at speed V. So we actually did this example in class just earlier today. So here's the test where it happened. Hopefully you get the same answer. I think oh yeah, I'm pretty sure that's the answer we got earlier today. Although one thing I missed in class because we were kind of out of time is that answer does simplify pretty nicely to this right here, because you can make a common denominator and stuff cancels a bit. So there's that. All right. All right, so that's the first thing for today. Let's see if I can find anything else to show you guys. So that was my test 3 from 2011. Here's my test 3 from 2013. Let's take a gander at this one. And if I'm solving some of your homework problems at the moment, my apologies. Probably I'm not. But, okay, so you got a uniform current of 37 microamps in a very long wire flows into the page at 1, 2. Find the magnitude and standard angle of the magnetic field due to the current at the point -2, 1 meters. So the way this works is the current is flowing into the page here, right? Boop. And so as your right hand comes around, you know, and you do the radial vector from here over to the field point, from the source point, so source current field point, you go perpendicular to the radius arm. That shows you the direction of the magnetic field because it wraps in circles around the current flowing into the page. And so geometrically, well, this is 45 degrees because that's 3 from here to here, and that's 3 from here to here, so that's a 45, which means you're 135 in terms of the standard angle for B. So there's the standard angle, 135, and then the magnitude is mu naught I over 2 pi r, which happens to be 7.44 times 10 to the minus 13th Teslas. So there you go. Or 1.744 picoteslas. Okay, great. Hey, this example we did not work this in class. We worked the solid wire. Here's a hollow wire problem. Ooh, fancy. So steady current flows along a solid hollow wire. It sounds like a contradiction, it's a solid hollow wire. But the deal is there's a hole, radius A1 in the center of the wire, and then it's solid metal, let's say from A1 all the way out to A2, all right? And you're given that the current is flowing uniformly, through the whole wire, and assumably into the page, let's say. So what we do is we draw an Amperian loop, a distance r from the center, and that allows us to find the current, the magnetic field. So, but first of all, I have to figure out what's the current enclosed by that, Amperian loop of radius r. This J is the current density. It's the current per unit area. So the area here is the area of the annulus in total, which is pi a2 squared minus pi a1 squared. That's the current density of the whole annulus. And as such, the I enclosed would be the current density times the area shaded, which is actually that. And so there you go, that's my current enclosed. This should be very reminiscent of like the hollow charged sphere problem we worked before, Anyway, so once we have that, then Ampere's law says that the circulation of the magnetic field around the Amperian loop is equal to mu naught times the current enclosed, which in this context is B times 2 pi r equal to mu naught times this business over here. So you solve for B, and you got this. And of course, if the current's flowing into the page, we're talking about magnetic fields that are circular flow lines, circular integral curves, as usual. But yeah, there's that problem. So by the way, like the first test we looked at, I probably gave during a lab period where we actually had like 2 hours to do the test. This is probably from like a Monday, Wednesday, Friday class, because I see it's only 3 pages. Or maybe it's from a Tuesday, Thursday class, and I was just super lazy. I don't know. But what do we got here? A loop travels from left to right as pictured. Beep, bop, boop, bop. In case 1, it's entering the region with a magnetic field out of the page. In case 2, it's completely inside the region. In case 3, the loop has partially exited the region with a magnetic field. Find the direction of the induced current in each case and or state the induced current is 0. So, all right, let's think about it. As it's entering the thing, the flux from the given magnetic field is increasing out of the page, right? So the induced current has to be opposite that to try to undo that increased flux out of the page. So we would have a clockwise induced current in case 1. In the middle, the flux is not changing, so the induced current is 0. And then in case 3, you're exiting, so you're decreasing the flux out of the page. So to keep it the same, to try to maintain the flux, you want to have a counterclockwise current like this in order to increase the flux out of the page, so counterclockwise. And these are all by Lenz's law. Well, really case 1 and case 3 are by Lenz's law and the right-hand rule. The middle one is just kind of like, duh. But nevertheless, students do find a way to not get that right. Like it's very, students get this problem wrong. They do. You might see me talk about it and think, oh, okay, that makes sense. But, well, yeah. Okay, so that's an LC problem. We haven't got to those yet. Here's the velocity selector problem. I think I recycled that one we already talked about. 100 Teslas, yowzers. Yeah, no kidding. Okay, we haven't done those yet. We haven't done this yet. State Maxwell's equation. Oh, and we're done. Yeah, okay. Wow, that was kind of an easy test. Let's see here. All right, I guess I'll show you guys one more test and we're going to call it a day. Or maybe I'll find some other old homework to look at. Well, no, that's not the one. Let's see here. Well, I guess this one's good enough to look at. I think this is actually my test from when I was an undergraduate. Yeah, you can tell this test is ancient because it's got typewriter. Look at that, like it's produced with like a mimeograph or something. This is like pre-computer produced test. This is pretty old. But okay, so to start with, we haven't covered this yet, so I can't talk about that. Sorry. And optics, we may or may not cover. I can't remember. This one's easy enough. Calculate the magnetic flux through the surface due to the constant magnetic field B. So we're given that angle's 30 degrees and the magnetic field looks like that. I think this problem was given in the problem. Or I've lost track of self. Anyway, maybe I don't know what happened. Anyway, so, oh, come on. Seriously? Come back. Come back to us. Come back to us. There we go. So B dot A, but that's cosine theta, which is 60, so BL squared over 2 is the flux. All right, great. Problem 5 here. Suppose you've got a cylindrical solenoid of length 50 centimeters, and it has 1,000 turns per meter and a total length of, well, like I said, 50 centimeters. Suppose that the radius of the solenoid is 10 millimeters. What's the self-inductance of this? Oh man, we don't know self-inductance yet. Rats. I'm sorry, guys. I'll stop this. State Maxwell's equation. Yeah, that's true. That's another story. We will eventually learn that the formula for potential energy stored in an inductor, if the inductor has a current I going through it, 1/2 Li squared is the formula for the potential energy stored in an inductor. So if I have 10 microjoules of energy coming from a current of 2 milliamps flowing through an inductor, it means that the inductance must be, 2 times the energy divided by the current squared, which gives me 5 henries. Yeah, the unit, my sister-in-law thinks this is very funny. The unit of inductance is a henry. Just kind of a weird name for the unit. Anyway, case 8, problem 8 rather, find the direction of the induced current for each case illustrated. So if the, let's see here, in each case the magnitude of the magnetic field equals to G of T. So I've written the direction here, and I'm giving how the magnitude is changing. Magnitude increasing, magnitude decreasing, magnitude increasing. So if the magnitude's increasing in the downward direction, then that means that I need to have the current flow in this way to make an upward opposite magnetic field for the induced magnetic field. So I need, and so this is the answer. Yeah, I guess it would be helpful if I also had the test without the answer written on it, but oh well. I can only project one thing at a time. But the answer, of course, the I was not given in the problem statement, right? Like the problem statement just has the B and the DG part, and the current I've drawn on afterwards as the solution. All right, this is the induced current. So here, if the magnitude's decreasing, you want to have the induced current in the same direction, in this direction, to increase the magnitude up. So that's why the current has to go like that. And then here, again, the magnitude is, increasing in the direction upward to the loop. And so I want to make the flux decrease in that, so I make the induced current go the opposite way, so it gives me a downward flux. So Anyway. Let's see if I have any other interesting problems in here. LC circuit, yeah, we don't know that yet. Man, I guess we need to get onto our LC circuits pretty soon here, huh? First we got to cover inductors though. I guess we could talk about this one, although I haven't introduced the pointing vector yet. So to find, I give the electric field and the magnetic field, and I have part A, what's the force on a charge, right? Well, QV cross B plus QE is the force, and so you calculate the cross product, and there it is, all right? Calculate the pointing vector, and what that is the pointing vector actually points in the direction in which the electromagnetic field is going. Electromagnetic field is formed by an electric and a magnetic field, which are both oscillating one into the other. And E cross B actually gives you the pointing vector, and it points in the direction in which the electromagnetic field is traveling. So I do E cross B to give me the pointing vector, and you also have to divide by 1 over mu naught. That's the definition of it. And so it works out to be that. Great. And then you can also talk about propagating electromagnetic waves, but that's a story for another day. Let's see here. Uniformly distributed current I flows through a wire of radius A. If the wire is very long, find the magnetic field due to the current, a distance r away from the center axis of the wire. All right, so we think about an Amperian loop. The current enclosed is pi r squared divided by pi a squared times I, because this is the fraction of the area which you're encircling. So that gives me the current enclosed. And then, of course, by the symmetry, it's just b times 2 pi r on the other side. And lo and behold, I get mu naught IR over 2 pi a squared for r less than or equal to a. And if we're beyond r, maybe I think that this should be a. This should be r less than or equal to a. I don't know what's wrong with me here. A is equal to r, apparently. What? Come on, guys. Man. Anyway, that obviously is supposed to be big A, and that's supposed to be big A as well. We've got it over here. I mean, this is radius A, so that divides the cases. Either r is less than big A or r is bigger than big A. Anyway, so if r is bigger than big A, little r, bigger than big A, then the Amperian loop contains the totality of the current, so you just get mu naught I over 2 pi r. And of course, the direction of the magnetic field lines are like this, so they encircle the axis of the wire. Optics question, I'm gonna skip it. Okay, so that was my test. Let's see here, that was test 3 from, goodness, when was that? Well, for me, it was originally 1998, but I think I recycled this when it's hard for me to tell which. I'm having trouble figuring out which of these. I think this may be from the first time I taught the course, honestly. Let's see here if I have anything else to show you. Oh, here we go. I guess I'll show you guys this one. Hopefully this isn't the problem I've assigned you in your home. Oh, wait a minute. Oop, I better not do that. Let me just check something right quick. I don't want to actually show you the homework I've assigned you. That would be bad, right? You don't want me to do that. That would take the fun out of it. So mission 6. 6.3 ohms, 2.5 Tesla magnetic field. Oof, that was close. I almost showed you the solution. We don't want that. Ooh, that was a close one. Anyway, have a good weekend, you guys. Listen, if you have any requests for problems for me to work for next week, just let me know. Thanks, guys.